and welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today we're going to be going into a new chapter. We're going to be looking at something called a response surface. It's not so much an experimental design as it is an optimization technique, and we're going to be doing that in this lecture. So the response surface is actually an experimental design, but its goal is a little bit different than what we've been doing so far. Its goal is to actually optimize the output of an industrial process. So there are many different things that you might try to optimize the output of, say, machinery, the amount of product you can extract from something. But ultimately, right, the idea is that we're going to have a lot of inputs to our machine, and we want to know what factor settings are going to give us the best output. And that's what we're going to talk about today in response surface methodology. So let's go take a look at the notes.
And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today, we will be starting an entire new chapter in my lecture notes, and it's on response surface methodology. This is going to be a little bit different than the things that we discussed earlier in the course, because earlier in the course, our main goal was to set up an experiment where we test various experimental factors, we control for variation and other other variables using blocks. We talked about things like replicating experiments, things of that nature, randomization. In the response surface methodology, or I should say, our goal of the previous was to more or less find out what factors are significant influencers on the output or response variable, very often a yield or otherwise in some of these agricultural data sets. But similarly, we have an output and we want to know, well, how does factor A affect the output? How does factor B affect it? And so on. In the response surface setting, the goal is different. The idea is that we have some industrial process. We're trying to make something, produce something, some kind of yield is coming out. So again, much like in the agricultural setting, we have a yield, but the goal is to figure out the factor settings to maximize the yield. So this is actually an optimization technique. It's very different in that sense from what we did before, but why are we doing this in design of experiments? Well, the idea is that we're not just going to be trying to optimize our process at random by trying lots of different settings. We're going to very carefully choose our factor settings in order to optimize our process, or in order to gain enough information to have a good choices to optimize the output of our process. And if you're imagining running the image I always have in my head is you're running some big machine, right? And you can set your dials. Maybe it's things like temperature and pressure and who knows, humidity or other settings. And you want to put the settings in just the right way, set all the dials in the best place possible so that the machine spits out as much output as possible, whatever we're producing. Now, it might take some effort to run one of these experiments, right? It's, every time you run one of this, you're expending resources, and you don't want to just test this thousands of times. You might only be able to test it a handful, like 20 times. And that's what we're going to look at. How do you choose the 20 best data points, or the best data points of some small number, in order to understand how the inputs affect the outputs? And that's the response surface methodology, and that's what we'll be doing for the next couple, I guess at least maybe, say, 3 lectures. So let's get into the notes and see what response surfaces are all about. As noted, what we have here is that this is called a response surface methodology. And it's a response surface. Well, what's a response, right? A response is a variable like y. And what we want to know is we want to understand the surface. So if that's not a terrible axis. They're not lined up at all. Let's do that better. If we have y, say, and then we have some factor, let's say x1 and x2, then what we're really trying to do is we're trying to figure out how does the response variable y depend on x1 and x2. And we're doing that so that we can find a specific point, a setting of x1 and x2 that will give us our biggest output for y, or our smallest, or whatever we're trying to do. The usual way you would phrase this is trying to maximize the output, but equivalently you could try to minimize an output if you really wanted to. So mathematically, the idea is that y is going to be some function of its input variables. In this case, we're going to have k of them. So what we have is we have our response. We have our inputs. We have an unknown function. And because we're in stats class, we have random noise. Right? Maybe if you're doing modeling in another class, you don't have to deal with random noise, but this is random noise. This is a stochastic optimization tool. In fact, it's no, I don't have it here. It's back in my office, which I haven't been to in many months now. A book on stochastic optimization from my master's degree. There's lots of different tools for stochastic optimization, which is I want to do optimization, but I have noisy measurements. It's a hard problem. This is one specific tool, and one whose goal is to, again, very carefully select the points where you sample from. Right, so what are we doing? Well, I'll say roughly, the goal is to fit a degree 2 polynomial to the data points, which I haven't told you how to collect them yet. There's two problems. One is how to pick your data points, and then how to analyze them. Well, this is kind of the how to analyze them. What we want is a degree 2 polynomial, which is a quadratic surface. And a quadratic surface, well, it can look a couple different ways, but hopefully it's going to look like some type of, see how well I can draw these things. It's going to look like some type of parabola. I guess this one's going the wrong way. This would be a minimum. Let's say we're trying to find a minimum, then I can find the minimum at the bottom of my parabola. Yeah. I'm not the greatest at drawing these things, so we'll see how we get through this on one note. But roughly the idea is that, okay, I have f. F is a complex function, or not complex in the complex number sense. It's a complicated function. We don't know exactly how the inputs depend on the output, or how the inputs influence the output. It could be linear, it could be quadratic, it could be some other crazy thing. But one of the great things about functions is that if we assume that it's smooth, then locally it probably will look sort of linear or quadratic, and that's what we're going to use. We're going to fit a low degree polynomial surface to our data, and then we're going to find the optimum, because if I have a degree 2 polynomial surface, I can find an optimum. I can find a critical point, which hopefully will be an optimum on either a minimum or maximum. There's a chance that it will fail. We'll talk about that when we get there. But that's roughly what we're going to be doing. I actually like this section. I find it really cool. And there's some really neat design of experiments aspects that we'll be getting to. So, okay, well, there's a couple things we have to do first. Step 1, or maybe this is like step 0, is we have to encode our factors. Because if we have factors that have crazy units, like let's say temperature might be like hundreds of degrees, whatever, pressure would be pascals, I guess. I don't even know what the right unit of that would be. But the idea is that you could have very, very drastically different units, which can affect your analysis if you don't standardize them. So what we do is we encode our factors. We standardize them. So There's a couple things we have to note. Typically, we will work with 3 level, or 5-level factors. So an example would be temperature. So like I said, let's say we want to set our oven temperature. We could set our oven temperature in Fahrenheit to, I guess in centigrade as well, but let's say Fahrenheit to 325, to 350, or to 375. Like when we were looking at that cake experiment data in one of the assignments that was that an assignment? Yeah, I think that was an assignment I gave you, the cake experiment data where you have different oven temperature settings. Now what we need to do is we need to encode these with some numbers. And what we'll end up doing is we will encode them typically as just -1, 0, and 1. These are going to be our 3 levels. It's a little different than what we talked about in the last section. In the last section, we were keeping it general enough to consider categorical variables. In this section, everything is ordinal. Which means that everything's going to have they're going to be numerical values that can be ordered, because ultimately the best temperature setting might not be 325 or 350 or 375. It might be something in between those numbers, and we're going to interpolate between to find the best temperature setting. Again, the hypothetical example, though we will look at some real data later so you can get some idea of what's really going on here. Anyway, this is a typical way that we would try to encode a 3-level factor. We would just assign it to the points -1, 0, and 1. Now, what if we had 5 levels? Well, if we had 5 levels, let's say we'll just do 300, stick with the 25 theme, 325, 350, 375, and 400. So if we had 5 levels, what we can do is we can encode them. And what I'm going to do is I'm going to say alpha. I'm not going to tell you what alpha is yet. Alpha is going to be some number for some alpha greater than 1. Like, say, 1.6 or something. And the idea is that we can choose an alpha value, which is going to give us 2 more levels to work with, one on the left and one on the right. So what this might look like if we were to draw a picture is that we might have, say, 2 factors, encoded factors, x1 and x2. Right, this is the plane that I kind of drew up here, right? We have the x1 and x2 plane, and we're trying to find the values of y, but we have to figure out where to put our data points first. So we could, for example, well, let's do some notches here. We could have, let's say, 1 and alpha, and -1 minus alpha, and 1 and alpha, and -1 and minus alpha. So for example, we could just pick some data points. We could pick, for example, 1, 1 and 1 minus 1. We could pick points on the square here. We could pick a point on the axis like these. We could pick center points. We could pick alpha crossed with alpha, right? There's lots of different points we could pick. In this case, we would have an alpha, alpha. This would be a 1, 1. This would be a 0, 0. This would be, I guess, a 1 minus 1, and so on, right? So the idea is that we have a plane, or we might have 3 or more variables as well. But for the sake of drawing it out and explaining it, we have a plane, we have two variables, and we need to pick some points as to where to sample from. Now, again, we encode x1 and x2 to just take on values like this so that it's easier to work with mathematically, and everything's on the same scale, because otherwise we might have temperatures in the hundreds, we might have pressures in like the tens or the ones, and it would distort this entire thing if we don't scale it. So what we're going to do is we're going to try to keep it on a scale like this. And this would be what a design might look like. Now, not exactly, this isn't exactly a good design, but it is what a response surface design might look like. It's going to be a bunch of points in the plane, or in 3 dimensions or 4 dimensions if we have more inputs to our model. So now that we have an idea of roughly what's going on with the response surface, what we're going to do is write down a couple models, because again, what I told you up above is that we want to eventually fit like a quadratic surface, but let's not get ahead of ourselves. Let's just write down a linear surface and see what happens, a plane, that is. So what we're going to consider is we're going to consider first and second order models, i.e. polynomial surfaces, where 1 is a plane and 2 is a, I guess, quadratic. All right, so what would this look like? Well, the first order model, is going to look like y is going to be some beta naught plus the sum I from 1 to k of beta I xi plus epsilon. So if you stare at that, you're going to think to yourself, that's linear regression, right? Yeah, that's linear regression. So this is just like linear regression. Except that in this case, we'd be carefully choosing the inputs xi to our model, rather than often when you apply linear regression, you're just given some inputs and outputs. Like I go and collect the heights of a bunch of people, I collect the weights of a bunch of people, and I try to figure out how weight is related to a person's height. How much do people get heavier as they get taller, for example, on average? In that case, I can't specifically choose people's heights. I mean, at least I don't want to. That seems kind of unethical. So, or weights, or vice versa, right? You just kind of get what you get when you sample your data. In a designed experiment, we're going to specifically choose values for our inputs. But besides that, it's effectively just linear regression. Now, what we can do, though, is, so what we can also do is we can consider the second order model. So the second order model is going to look like y is going to be, well, the first order model, right? A second order is going to include the first order, which is a linear combination of my data points, beta I, xi. But we're going to get a couple more things. We're also going to get a sum. I'm going to say I less than j. This means sum over all the pairs of indices where I is less than j. Beta ij, xi, xj. And we're going to get the diagonal terms, which are going to be I from 1 to k of beta I xi squared, and then we're going to get epsilon, our random noise, as we always get. So we have a couple different things going on here. We've got the constant intercept piece. We've got the linear piece. We've got interactions. And these are sometimes referred to as pure quadratics. Quadratics, close enough. So yeah, the interactions are technically kind of quadratic in the sense that you're multiplying two variables together, but they are treated statistically a little bit different than the pure quadratics, which are these x squared terms. So this is all different ways that the output y can depend on x. Well, first there's going to be a constant mean or intercept term, beta naught. Then there's going to be a linear term. So as x1 changes, y is going to change depending on what beta is. There's going to be interactions between x1 and xi and xj. In this case, I'm actually just multiplying. We're done with all these for the moment with these like abstract interaction terms. Here, I'm literally just multiplying xi times xj together. And then the quadratic term I'm squaring. So we're not doing again. This isn't like one of those group theory things that we were doing in the previous lecture. Here, we're just dealing with real numbers. Xi is literally just being squared, and it can that it's going to tell us, the beta ii's will tell us how the response behaves quadratically in the x's as x changes. So we can write this out in a cleaner form. We can write this in three pieces. We're going to get a beta naught, which is, again, the constant term. We're going to get an x transpose b, little b. That's the linear term. And then we're going to get an x transpose big B x, and then there's always a plus epsilon, which I think I left out of my lecture notes, but that's okay. It's always there. So here again, we have the constant, the linear, and both quadratic pieces represented here. So what we have is we have that x is just a vector of x1 through xk. These are our input points. These are our predictor variables. The actual settings of them will be our input points. The vector b is just going to be a vector of betas, beta 1 through beta k, how the response behaves linearly in the x's. And then big B is going to be a matrix of betas. In this case, I guess the diagonal entries are going to be not big B, but beta 1, 1, beta 1 or 2, 2, all the way down to beta k, k. And the off diagonal terms are going to be beta, we can enforce, I guess we want I to always be less than, we can do it two ways. We can just write it as beta 1, 2, beta 2, 1, but we have to divide each of these by 2 to make the math work out. So this maybe it's going to be easier if I write this outside of the matrix. The off diagonals are beta ij over 2, which are also going to equal beta ji over 2. The reason is because if we multiply on the left and on the right by x in this quadratic form style, then what we'd end up with is, we'd be adding each term twice, and up here we just have a beta ij. So what we really want is we want beta ij over 2 plus beta ij over 2, so that we just end up with a beta ij. If you actually write out the quadratic form, you kind of see how the two terms combine. And just for notational convenience, we'll assume that if I flip the indices, I get I and j, I get the same thing, just so I can write this out as a big matrix, a symmetric matrix, by the way, which is always a good thing to have. Thanks to the spectral theorem and many other reasons why symmetric matrices are just fun and pleasant to work with. All right. So, again, the idea is pick some points, then estimate, or I should say fit, the second order model. Because I have this is a linear model, so this can be a little confusing, because linear in mathematics means, well, linear, like a line or a plane or something. But strictly speaking, this entire thing is still, well, no, it's still a linear model in the sense that I have inputs, k inputs here. I have, I guess, k minus 1 choose 2 here, and I have another k inputs there. And I'm linearly combining them to get the response y. So ultimately, we can given the data points, when I say fit a second order model, I mean compute the least squares estimator for the betas. Because I have a model, I have a bunch of parameters. If I have enough data point correctly chosen, I should be able to estimate all of these betas, and then I just get my beta hats. So let's pretend that we did that. And then what do we do? So the idea is that, assuming we estimated the betas by beta hats, we use calculus, or I guess R does it for you, but on paper we use calculus to find the critical point, of the quadratic, I'm having a hard time spelling that today, surface. There's an inverse relation between how excited I am about math and my ability to spell. So yeah, when I'm in a lecture I like, typically I'm probably going to be making spelling errors all over the place. Anyway, how do we solve for the maximum of a quadratic surface? So again, if I start with the idea that y is equal to beta naught plus x transpose b plus x transpose bx, and in this case, I'm not putting the epsilon in, and I'm going to put hats on everything, because now we just have a fitted surface. So again, I estimated my parameters, I can shove them all into the model. Now I have a quadratic surface, so let's do some multivariate calculus. All right, so if we want to find the critical point of a quadratic surface, we're going to do some multivariate calculus. In this case, what we basically do is we, well, take a derivative with respect to x and set it equal to 0 and find the critical point. Now, what we end up with is an equation that's going to look like, well, when we take the derivative of beta naught, that's constant, that becomes 0, that doesn't do anything. When we take the derivative of the second piece, so I'll write the 0 in just so we can see where all the pieces go. We're going to have a b hat when we take the derivative with respect to x. For the quadratic term, it's a little bit different. We end up with a 2 beta hat x. This is the, I guess, shortcut of not actually writing it all out in terms of individual terms. But if we wrote it out in terms of these individual terms, we could try to go through it that way. But this is kind of the fast vector way to do it, because what this means is that we end up with a solution which is going to be x. What notation was I using? I was using xs to be the, why did I think x? Oh, stationary or critical point. So x sub s is going to be the point that we're looking for. Remember, a quadratic should have one critical or stationary point in it. And what that's going to be is it's going to be something like minus b hat inverse times vector b over 2. So remember, this is still a matrix and a vector. That is, oh, I need a hat on the b, little b. So again, yeah, big B is a matrix, little b is a vector. I'm doing a matrix vector multiplication to find my critical point. Yeah, if we really want, we could write this all out with like gradients and stuff. I don't really want to do that because I'm not here to do a multivariate calculus. We're here to do a response surface. But if you do have any questions about this, again, let me know. We can always talk about it and make sure that this is all clear. But roughly the idea is that I have a quadratic surface, there's one critical point, and that's what it is. Now, again, this is an estimate for the critical point. It's not the it's not the optimum or the critical point of the true surface. It's the optimum or critical point for the estimated surface. So again, we're still doing statistics here. But B is going to be actually really important. So B is symmetric, as I mentioned before. Therefore, by the spectral theorem, if you recall your, I guess, advanced linear algebra, don't worry if you've never heard of the spectral theorem. It basically just says I can decompose B into a matrix multiplication that's going to look like U transpose du, where U is the orthonormal matrix of eigenvalues, and D is the, no, not eigenvalues, eigenvectors. And D is the diagonal matrix of eigenvalues. Right, so this is just the way an eigendecomposition of the matrix B. I guess the spectral theorem 1 says that we get these orthonormal matrices out, and furthermore, the eigenvalues are all going to be real. And that's good, because the eigenvalues are going to be important. The eigenvalues are going to be, we're going to denote them as lambda 1 less than or equal to lambda k. So we're going to put them in decreasing descending order, right? These are going to be my k eigenvalues. There could be ones that are equal to each other. They could be positive. They could be negative. But this is what we get. And this is going to be important in a second. So let's just kind of keep this in mind, because this is going to tell us, the matrix B is going to tell us what type of critical point XS is. To see that, let's see what happens to our fitted value y hat around the critical point. So what happens to fitted value y hat around XS? I think I was just using XS, the critical point. Well, let's just write that out and see what happens. So in general, going back to the equation we had above, that's right, I should probably write a y hat up here, just to indicate that this is in fact a fitted value and not a real value. It's not an observed value of y, it's the fitted value from the fitted model. All right, so we have something that looks like this. Just to rewrite this same thing from the top of the screen down here at the bottom of the screen. I need to transpose on the x. So what we're going to do is we're going to rewrite, we're going to basically shift the origin, right? Right now, when x is set to 0, we're at the, I guess, the origin in our Cartesian coordinate system. Instead, what we're going to do is we're going to replace x with xs plus, I think I was using z. So xs is the stationary point, and then z is going to vary. So basically, we're shifting the origin to the critical point or the stationary point for our quadratic. Well, what happens if we do that? What happens is we get something that looks like xs plus z transpose b hat. xs plus z transpose big B hat xs plus z. All right, cool. Right, so we have those, right, we have this thing. So what can we do with that? Well, what we can do is we can expand, we can kind of separate the x, s, and the z. And what we get is we get the original equation all in xs. And we get the equation in xz. It's okay. It's not too exciting yet, but it's going to get exciting in a second. So just stick with me a little bit longer. We get this thing. Then what we get is we get a z transpose b hat. We get a 2 z transpose b xs. In this case, remember that B is a symmetric matrix, so if I multiply X transpose BZ is equal to Z transpose BX because it's symmetric. Actually, no, it's a quadratic form. No, no, B would have to be symmetric or else it wouldn't work. I was going to say, of course, it has to be symmetric for that to make sense. But yeah, as a result, that's where the 2 is coming from. And lastly, we get a Z transpose B Z. Okay, so what happens here? Well, the first thing to note that's important is that here, this whole thing is going to be, we're going to call it YS. This is the value of Y at the stationary point. Okay, so what happens to the rest of this stuff? Well, okay, this is actually quite interesting. We have something here that looks like Z transpose B hat 2 Z transpose BS XS. So let's look at this a little closer. Well, this is going to be, let's see, if I factor out the Z transpose, this is going to be Z transpose B hat plus 2 B. I keep forgetting to put hats everywhere, but there should be hats everywhere. If I forget a hat, there should be hats on all the B's. Okay, so it's Z transpose times, in parentheses, little b hat plus 2 big B hat times X. We've seen that before, haven't we? Didn't we just see that? Yeah, that's up here. And you know what it's equal to? It's equal to 0. So actually, this whole thing is 0. Oh, that's great. And then we're just left with this last little bit, which is Z transpose. This guy is still here, which is Z transpose B hat everywhere, Z. So what we're saying is that the behavior of Y hat, the fitted value around the stationary or critical point, depends only on B hat. Well, a quadratic form involving B hat. So this is important because we can then use the eigen decomposition. We are going somewhere with this, so there is a point to all this. We're going to use the eigen decomposition here to rewrite this as Z transpose U D U. I forget where I put the transpose. U transpose DU. It can be kind of vice versa. I'm going to drop that. I'm not going to put hats on the D and the U, but effectively they are the eigenvectors and eigenvalues of our estimated parameter matrix. So I guess technically they're estimates, but I just don't feel like writing lots more hats. Anyway, when we apply U and U transpose to Z and Z transpose, we're just doing an orthogonal rotation. So again, if you haven't seen this, basically U is an orthonormal matrix of eigenvectors. It corresponds to a rotation in k dimensions. So all I'm saying is I had a Z like this, I hit it with that matrix U, and then it rotates to a different position. It's a change in the basis in a sense. But it's not going to matter too much. We're just rotating things. So I'm going to denote that by V transpose and V. Right, I'm just condensing this into a new vector. And so again, it's just like a change of basis. We have a new vector in there, value, but it's kind of the same thing. But what this means is now we have a y, not hat, ys. And the reason why I did this is because now we just have a simple summation I from 1 to k, lambda I, the eigenvalue, v, that looks more like a nu. Let's do a proper v I squared. So what does this mean? Well, what this means is that the eigenvalues lambda are going to tell us what the surface looks like around the stationary critical point. So what this means is a couple things. We'll say 1, if all lambda I are less than 0, then we have a what? A maximum. Why is it a maximum? It's a maximum because if all of these lambdas are negative, then if I change any of these v's from 0 to anything that's not 0, I'm going to be subtracting something from ys. I should say at a maximum of ys at xs. So xs is the location, ys is the maximum value in this setting. Conversely, if all lambda I are greater than 0, then we have I bet you can take a guess, a minimum of ys at xs. Again, if all the lambdas are positive, then that means whenever I move any of the v's away from the point 0, I'm just going to be adding a positive number to y, s, which means it's only going to get bigger as I move away from my stationary point. And then lastly, there is the annoying answer, which we typically don't really want. The annoying answer is if some lambda I are less than 0 and others are greater than 0, we have a saddle point, which looks a lot like that saddle dome if you've ever been to Calgary. At least in 2 dimensions. In 3 dimensions and 4 dimensions, it's going to be a little bit harder to visualize. But we have a saddle point. That means in certain directions, the response increases. In certain directions, the response decreases. So if we're trying to maximize our process, we're going to have to look in the direction of increase and search in that direction for better data points. If we want to decrease, then we would follow in a direction of steepest descent. So ideally, we don't get a saddle point. Ideally, if we're trying to maximize a process, hopefully all our eigenvalues are negative. If we're trying to minimize it, hopefully all our eigenvalues are positive. If the opposites occur, or if we have a saddle point, we're going to have to find better inputs to optimize the process that we're trying to optimize. All right. Yeah, let's talk about, you know what we'll do? Why don't we talk about some response surface designs, specifically the central composite design. We'll do that, and then we'll save the rest for the next lecture, since after that very brief lecture on agricultural data, I'm now going on well, 75 minutes of speaking. So voice is still holding out a little bit longer. So the next big question we have is, okay, now we know about fitting a quadratic surface. But how do we choose the data points? I shouldn't say data points, the design points. Right, how do we choose the design points? Remember at the beginning of this lecture, I kind of showed on the plane, we can pick values like 1, 1, and 0, 0, and 1, minus 1, and things like that. But then the question is, well, what are the right choices, right? If I have 2 or 3 or 4 or k different inputs to my model, how do I choose these points, and how do I make sure I choose them efficiently? Because if k is big, we have a lot of different directions I can go in, right? And we have to be careful that we don't have too many data points, because every data point means you have to collect data at that for those settings, for those factor settings. And that means you need to, well, spend the time and the money and the effort to collect that data. So ideally, we want to keep the number of design points as small as possible, with still having the ability to properly fit a good response surface model. That is, fit a quadratic surface to our data. All right, so what are we going to do? Well, let's count. Note that the second order model has how many parameters? It has 1 plus k plus k choose 2 plus k parameters, which is going to equal, if you do the math and simplify it, k plus 1, k plus 2 over 2. Okay, so where's this coming from? Well, 1 is the intercept. K is the linear piece. K choose 2 is the interaction piece. And this other k is going to be the pure quadratic piece. So these are the different parts of the second order response surface that we have to estimate. So the first thing we have to know is that if we want to estimate that many parameters, we need at least 1 plus that many data points, right? So the idea is that, therefore, we need at a minimum, we're going to need k plus 1, k plus 2 over 2 plus 1 data points. But possibly more, to get a better fit for our model. Right? We don't want to necessarily just do the bare minimum, but it is a good thing to keep in mind that we have a certain number of parameters in our model that we have to estimate. So we need to make sure we have at least enough data points to estimate all of those parameters. We need at least 1 data point for each of the parameters in the model. In practice, we're going to need a few more. All right, so this leads into the first and the main response surface design that we're going to discuss. What we'll do is we'll introduce the idea today, and then we'll pick it up in the next lecture, and we'll go into a little bit more detail on why this model is the way it is, because it's very carefully chosen data points. All right, so what we're going to do is something called the central composite design. So the central composite design actually is comprised of 3 different types of design points. So we're going to have 3 types of design points. And those are the cube points, the center points, and the axial points. And each of these is going to have a very specific purpose in the model, and we need to include some of all of them in order to fit a proper response surface. I don't like the way I've outlined it here. So what we'll do is we will just kind of explain, well, one at a time. So first of all, we have this idea of cube points. So what are those? Well, those are going to be points that lie on the vertices of a hypercube. All right, that probably doesn't help explain it. What they actually are going to be is the variables. Well, it's basically going to mean, i.e., the xi take values that are either going to be -1 or +1. So that sounds a lot like a factorial, a 2-level factorial design. And yeah, keep that in mind. But yeah, basically the idea is that if I have my axis, maybe I can do this in 3 dimensions, why not? And we have something like x1, x2, and x3. If we have 3 inputs to our model, then what we're going to get is our cube points are going to always take on values of plus or minus 1. So I should have a point that is, I guess, oh man, I cannot do 3 dimensions. Let's do this. I guess like here, there's going to be 1 down here. There's going to be 1 over here, 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 there, and I guess 1 in the back somewhere that I forgot. So these would be the possible cube points that we can choose. Now, I'm not saying that we need to include all of them in our response surface design. The point is that we're going to have some number of these in our design. We could include all of them. We may not want to. Those are the cube points. So things to keep in mind. Looks like a 2 to the k design. But we may not need all of them. So the hint is maybe we're going to want a 2 to the k minus q design. A fractional factorial design instead of a full factorial design if we don't need all of those data points. But again, we'll get to exactly how to choose this design later. All right, so then we have the center points. And these are going to be, well, in the center, right? Yeah, these are perhaps the most boring points, but still serve a valuable purpose, which is xi is equal to 0 for all I. So the point is we pick these, or I shouldn't say we pick, we picks. We choose these to stabilize the variance what we'll see is that we need to choose center points to, I say center points because that's another thing I should point out. Often we repeatedly measure this point, I guess. So what that means is that unlike in just about all the designs we've looked at so far, where we just have a specific setting for our factors and we sample it once, and maybe if we replicate the design, then we sample everything a second time or a third time, in this case, we're going to replicate that center point 2, 3, 4, maybe 5 times. And by doing that, we're going to get a good way to estimate the variance of the underlying process that we're trying to fit our model to. I'll say i.e. replicate, but only this point. Which is kind of funny. We are replicating, but we're only replicating a specific point in our model, and that's the center point. The last type of point we're going to have is the axial point. All right, so as I mentioned, the last point we're going to have is the axial point. And the axial point are, well, points on the axes, or on an axis. That is specifically what it's going to be is, i.e., we're going to say xi is going to equal to alpha or minus alpha for some I, and xj is going to equal to 0 for all j not equal to I, which basically means it's going to lie on the ith axis. And this is going to be for all the axes. So if I were to draw my three-dimensional thing again with, I forget, x1, x2, and x3, then the axial points are going to be above and below, to the right, to the left, to the front, to the back. And they're going to take on some value alpha. This is what I mentioned earlier on. We actually have a 5-level factor in this case where we can take, where x can take on values of plus or minus alpha, where that's going to be some encoded value in our design. I think I encoded the design at the very beginning of the course slightly. Now I see what I did. Okay, it doesn't really matter. I just realized one little, well, I'll just fix it now. Okay, in my course notes, yeah, I forgot that one thing I actually did was I put a 310 and a 390 here. And the reason was to correspond with alpha equaling to 1.6. So there was a reason. So just to make sure the math worked out exactly right, I'm going back and changing that. We'll talk about this more when we do a real data example, and you see what I mean by encoding the values of alpha like this. I don't want to go into it right now because I'm going to save that for the data example. But all right, so now what we have is we have these, we have these 3 types of points, and there's a lot more that I want to discuss about that. But what I'm going to just do is leave you with a few things. So why do we need these points? Well, as I mentioned already, the center points are for the variance. The cube points are for the linear and interaction terms. And the axial points, the ones that are left over, well, what do you think they're for? They're for the pure quadratic terms. So remember, as I mentioned before, we need a certain number of data points to be able to estimate all of the parameters in our model, but we also have to choose those data points very carefully so that we can estimate each piece. And it turns out that these cube points are really good, or well, the point of them is to estimate the linear piece, which is the beta I and the beta ij for I less than j. Meanwhile, the axial points, the purpose of including them in our model is so that we can actually get a handle on the pure quadratic effects that are hidden in the relation between the input and the output. And lastly, the center points, in some sense, they do need to be there to actually to fit the model. Okay, we don't need them, but the problem is the variance will be all messed up and terrible. And this is to basically estimate sigma squared, which is from epsilon, which we'll assume, again, is normal 0 sigma squared. Because ultimately, you can think of the center points as replicating some center points in order to get a sense of what the residuals are doing, right? Much like we would do in the other designs, we always would have some degrees of freedom left over for the residuals. That's basically the point, kind of holistically, or it's not exactly the right, but it's intuitively, that's kind of the idea, that the center points are there to help us get a good estimate for the variance, and that's going to be useful because we need a good estimate for the variance if we're going to do any sort of significance testing on our coefficients, the linear, the interaction, the pure quadratics. Now, there's still a lot going on here, like, for example, let's just count it all. All right, let's just say that in this case, how many points in total? Well, if I have, let's say, C center points, I don't know how many, let's say I replicate that a few times. If I take all of the cube points, well, now I have a 2 to the k, because there are 2 to the k different vertices in a k-dimensional hypercube, which correspond again to those points up here, the green dots on the vertices. For the axial points, I would get a plus 2k. So the problem is that this grows exponentially in k. Meanwhile, this is the number of parameters remember is equal to k plus 1, k plus 2 over 2. Well, this grows quadratically, which is much slower than exponentially. Why can I not spell that today? Quadratically. Close enough. In k. So this is one of the problems that we have here with the central composite design. We have a certain number of parameters, and we know that they actually do grow fast. If the dimension gets bigger, we're going to have a quadratic increase in the number of parameters. So if we have like a model with 10 different inputs, a response surface model with 10 different inputs, that's a lot of parameters to fit, right? That's going to be 11 times 6, which is 66 different parameters. But if we tried to fit this model here, we would have something like 2 to the 10, which is 1,024, plus another 20 on top of that. So 1,044 plus however many center points we decide to replicate, which is usually like 2 to 5. So the point is that we have to, so the next thing we need to do is we need to reduce this if k is even a little big. And that's going to be what we'll be discussing in the next lecture, which is how do we carefully select the points in our response surface design, that is, in our central composite design, because there are other response surface designs that we'll talk about. But right now, focusing on the central composite design, how do we choose the right cube points and the right number of center points and all of that in order to be able to estimate everything without just wasting tons and tons of money and time and effort collecting extra data points. And it's kind of neat to figure out how this is going to fit together with what we learned about 2 to the k fractional factorial designs. And there's also some other really neat quirks that pop up as well in this. It's a fun subject, but we'll have to save some of this for the next lecture. I'll see you there.